All right, welcome back. We are Game 3001. That's Artificial Intelligence for Games in the winter 2022 semester at George Brown. And it's week 15 of our broadcast and recording. This is the last lecture that we'll have this semester. And it's all around the new stuff, machine learning in games, reinforcement learning, and Q learning, which is, some really great topics. And kind of a higher level topic in terms of complexity. And we'll talk about that in a bit. But first, let's talk about what happened last week. Last week, we discussed tactical and strategic AI. Lab 8, we added a ranged enemy attack action that you guys hopefully used in your final submission for your assignment 4. That was due yesterday. And what are we doing this week? This week, we are presenting your assignment 5, I should say, it's on Thursday, but the actual assignment itself, which is the PowerPoint slide deck and your all your video recordings, your pre-recordings and all that kind of stuff, that's all due tomorrow at midnight. So please make sure that you submit your assignment 5, before you present on Thursday. There's 2 parts, remember. The first part is all your materials and your pre-recorded videos and so on, and that's due tomorrow at midnight. Again, you'll be using A4 groups, so assignment 4 groups. To do that, there is no assignment 5 groups. It's because it makes sense that assignment 4 is going to lead into assignment 5, and that's why there's only one set of groups left. Okay, so again, presentations are going to be held on Thursday this week, and just for that, before we move on, the sign-up presentations sign-up sheet is on Blackboard. So let's go to that for a second. So if you go to your content under week 15, there is a final presentation sign-up sheet, which you can get right here. You can see that the groups are already listed here. So we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 groups. I think there's 17 total, so there's still 5 groups left to sign up. And if you haven't had a chance to sign up, please do so immediately so you reserve your spot. Again, these are the group times, and what's happening this morning is what's going to be managed by Alex, and then I'll be managing the groups in the afternoons. So again, please make sure you sign up if you haven't done so already. No sign up, and if you don't present or if you're late, you'll get 0 for your final presentation. We don't want that to happen, so that's why I'm giving you another chance to do so now as soon as possible. All right, so that's what's happening this week. It's your final presentations. Again, really looking forward to seeing what that's going to look like. And let's move on to the topics of today. So again, it's last week of class. As you can see, we've got a bunch of stuff to talk about. Some of the things I'm going to dive into. Some of the things I'm going to skim over because it might be pretty heavy duty in terms of the detail. One thing we won't have a chance to do, which is always, unfortunate, is we won't have a chance to practice any of this stuff, which is something that I've always wanted to do with you guys. And maybe in the future sessions, you might have a chance to do so in in a component of another class, maybe to do some more advanced artificial intelligence in some other course in the future. But what this is supposed to do for you, and this is why this is kind of the last lecture, is it's supposed to give you some ideas of where to go from here. What's next? What are takeaways from the course? This is what this is all about. So let's talk about machine learning for a second. Actually, you know what? Let's step back one step because I know there are people coming inbound. Any questions before I move on to machine learning? I want to do that first. Questions, concerns, anything like that before we move on to the next step. Because I know people may have questions. I know we were working with some students yesterday on assignment 4. I know assignment 4 is a bit of a beast in terms of what we've asked you to do, but it's been a kind of a progression the entire semester. And so the expectation is that as you kind of step through all the details, then from one assignment to the next, then you're supposed to be more challenged. It's more like layering things on top of what you've learned from the previous assignment. Assignment says, to be honest, I found assignment 3 bigger. Yeah, I mean, it was kind of a foundational assignment, and we gave you as much as we could for assignment 4. Really, you just have to kind of fit the puzzle pieces together, which is what we're hoping you would do. So that's where we were going with it. I know some people had issues putting together the decision tree and all that kind of stuff, and I think it's if you've gone through it at least once, it's a really great exercise. And the reason for this is it's directly relational to what you might be doing in a AAA studio or on your own. If you're an indie studio, making your own kind of decision making algorithms and all that kind of stuff. Now, again, going forward, you may not be using decision trees. You might be using something like behavior trees or state machines or something else. But the concepts that we shared with you for assignment 3 and 4 would be pretty much the same. These are things that are transferable. You can use in kind of a future course or a future project. Okay, so that's good, Simon. I'm glad that you didn't find it too crazy. Anyone else have any comments or questions around assignment 4? All right, let's then talk about machine learning a little bit. So, really hot topic nowadays. You might hear machine learning everywhere. It's a thing. There are specialty courses and graduate programs and all that kind of stuff on machine learning. But why is it so hot? And if I was going to talk about machine learning in a nutshell, how would I talk about it? And whenever I think about machine learning, in terms of what it does, I always think about it as an analysis tool on steroids. That's kind of how I look at it, right? So you want to do different types of analysis, whether you're doing some classification. I'm classifying what I'm seeing. This is a dog. This is a cat. I'm kind of classifying it based on the data set, the data that I'm getting in. I'm doing some kind of recognition and classification. That's one option. The other one is regression and prediction. So I'm kind of thinking about, okay, so now I'm seeing a trend. What do I predict is going to happen? Those kind of things are typically what I think about when I think about machine learning. However, when it comes to machine learning in games, it's a little different. Machine learning in use of games is almost like I want to have my tactical and autonomous character have the ability to adapt, to be more of a challenge for players. That's really what we want to use machine learning for. And we're going to talk about what it is and how to do it in a second. So again, what we want is these autonomous characters to learn about their environment or their game state, get rewarded for doing the right stuff, and then, kind of pose a more of a challenge, reasonable challenge again for players. That's the idea behind them. They become more realistic. And again, the more realistic our AI is, the more immersed we feel, the more we are in a state of flow when we're playing a game. If the AI is bad, like we've talked about in the past, it could kick us out of that sense of flow and immersion, and it will break our sense of disbelief in the game that we're playing. And it's like, okay, so this is a really bad AI. We might even laugh at it sometimes if it's that bad. So one thing that we've talked about, it's been machine learning in games has been talked about for a long time. For the most part, it's still not fully fulfilled, that idea of using machine learning everywhere. Commercial game engines like Unity and Unreal have components that you can turn on, as an example, to have to use machine learning for your agents. And one of them is ML agents for Unity. And if we look that up, that's something I didn't put in one of our links. So if you look at Unity ML agents, it's a very interesting. They have a toolkit that allows you to use machine learning. You can see here, this is a GitHub repo that allows you to combine machine learning with AI. And it's interesting, they have different pieces to it. One part is a Python requirement for Unity, which is kind of interesting. And they're going to continue to add more and more things to Unity and commercial game engines as we go. But for the most part, beyond commercial game engines, implementing machine learning in your games can be quite a task. So again, it's really, we want to create compelling characters, but it's less about that and more about challenge, right? So that's what we want to do. So again, there's a lot of different techniques we can use when it comes to machine learning. Everything from some number tweaking that we're going to see in a bit to very complex neural networks. A lot of times we hear this buzzword, which is like deep learning, which is another form of neural networks. And there's a lot of different kinds of approaches when it comes to how to implement machine learning to our character's behavior, our autonomous character's behavior. And we can classify, these learning techniques into groups depending on when the learning occurs, right? So when I'm going to kind of get the agent to learn about the world and about the player and all that stuff, and what is being learned. What am I teaching it? As an example. And how do I do that? How do I teach anything to anybody? Really, at the end of the day, if you think about it in real life, how do we do it? We have memory, right? When we learn stuff, when we do things that are good, we get this positive reinforcement, right? We feel good about ourselves because we did something good. We did something right. When you fix something or you create a piece of code that works exactly how you expected it to work, you feel good about it most of the time if you're a programmer. And if you make something that's constantly breaking, you feel terrible about it, right? That's kind of like the process of reward and a bit of punishment, in fact, when you don't do things very well. So this idea of reward and punishment is how we can train our autonomous agent to do the right things, okay? And it goes beyond just simple decision making, like, for example, the behavior tree or decision tree or goal-oriented behavior or utility AI or any of that stuff that we've talked about so far. This is a whole different area of artificial intelligence. So let's talk about two types. There's online or offline learning. Okay, so online learning, it can be performed during the game, so that's in real time while the player is playing. So it allows the autonomous characters to adapt dynamically to the player's style and provides more consistent challenges. As the player plays more, their character's traits can be better anticipated by the computer. So for example, they're profiling you as you're playing. They start taking a look at what you're going to do, and they start predicting. The AI agents start predicting what you're going to do if you're very predictable. And a good example of that is if you constantly, like we talked about before, for the machine learning, for decision making, if you constantly pop behind cover and wait for exactly 1 second and then come back out again, if you have a very predictable pattern of behavior, that's the easiest thing for machine learning agents, ML agents, we'll call them for now. They're able to predict. They kind of look at your behavior, okay? So we're going to kind of create enemies that have this ongoing challenge for the player, and it could be used to offer the player more storylines, depending on if we want to procedurally create, kind of context and story. That's something else we can do with online learning. So something that's happening in real time. Disadvantage of online learning is it's really difficult to predict what's going to happen, and it's super difficult to test if what is happening is what you plan to happen. How do you test that? Because what's happening is the online machine learning agent or ML agent is making some decisions, and the debugging that's involved in terms of did they do the right job. I mean, I don't know if you guys had the same issue when you were trying to debug your A4. So I have my decision-making algorithm, and it's supposed to either do a flee or a move to player or move to line of sight or one of those things. And kind of debugging even that little decision tree could be quite difficult. Like, what is happening? Why is it happening? What are the values? How do I stop that? The whole making a decision function that we gave you is a big while loop, and it's hard for you to create a breakpoint that's going to give you any valuable information. Okay, so that's kind of how it works. So can you imagine something where the agent is learning? You've given it some free will, if you will, a little bit, or it appears to be free will. It's not really free will, but the idea is you're giving it some agency, all right, some control of its own actions. Sometimes those actions can appear, by the way, pretty wacky when it learns the wrong things, right? Or if it gets stuck. But for the most part, you got to figure that how do you confirm, how do you validate that an online agent is doing what it's supposed to do? Planned versus actual. How do you do that? It's tough. So then there's offline learning, which is really the majority of machine learning in game AI. It's all done offline. And what this means is it's given a set of data, right? And it learns about the world offline. Sometimes we have it so that it is working on, kind of explores the game state on its own. So there's no player, it wanders around the world. You let it loose to wander around the world. You train it over several epochs or eras, if you will, and it spends its time, over a course of you give it a time limit, and it continues to explore the world. So it knows things like the best hiding places, the best ambush locations, where resources are, all that kind of stuff, right? So way ahead of time, it kind of understands and it notes all this kind of stuff. So when the player comes into play, then it can respond by, hey, I know where my resources are. I know where I can get a health pack, right? Because I've explored the world. I know, where this is or where that is in the game world. And it's really interesting how autonomous agents work in that way. So it's more predictable and it's more testable because we can give it things like, hey, here is a set of conditions, and what have you learned based on that we've trained you how to do certain things. You should know where the health packs are and the ammo packs are in the game world and the resources for, kind of building up, your if you need resources to build something in the game world, you know where all that stuff is because we trained you. Let's see what you do. Did you actually do the things that we've taught you to do? So things like accurate pathfinding. I want to know how to, kind of find my way around the world. I know where the obstacles are in the world. I know how to do obstacle avoidance. I know where I have friends, in the world that can help me out to do more tactical AI. I know all those kinds of things. So again, the challenge with this is it's still in experimental phases in terms of how many studios out there use machine learning, especially things like with offline learning, to create autonomous agents. It's rare, and the games are few, okay, in terms of how they've been successful. Sometimes it's only used in certain parts of the game, right? For example, Ubisoft always talks about their LaForge R&D studios, both existing here in Toronto and in Montreal, and they talk about how they use machine learning agents to kind of walk more naturally, to be able to navigate, around a crowd, those kind of stuff. So kind of crowd simulations and those things to make the game more immersive and more realistic. That is also another way you can use machine learning. It's not just about pathfinding and tactics. It's not about that. We can also use machine learning, whether it's offline or online, for procedural world generation. That is also something we can do, where you can test to see if you have kind of the right conditions to create a world that's layered and that's contextual for what you want to try and create. So you can actually test the world to make sure that it meets your criteria with machine learning. Again, categorization, classification, and separation. You want to separate. I have this much grass and I have this much land. Does this meet the requirements? Can I regenerate the world or reiterate on it? I'm thinking Minecraft or something like that. Again, one of the newer ones might be Core Keeper, where you do procedural generation and you kind of figure out if the world works as it should. So that's another way you can do it with offline learning. So there's two types of, we're going to talk about different learnings. One of them is intra-behavior learning. And then like it sounds, it's something that's happening inside the autonomous character themselves. So it's the simplest kind. We want to change a small area of the character's behavior. They don't change the whole quality of the behavior, just a small amount. We simply tweak things a little. And intra-behavior learning, it's easy to control and can be easy to test. Here are some examples. We want to learn to target correctly with projectiles, when they're modeled with accurate physics. How do I do that? So I learn how to use projectiles that are, let's say, things like grenades that are lobbed or something like that. We want to learn the best patrol routes around a level. We just talked about that. So we learn those kind of things. where the best cover points are, and how to chase an evading character successfully. You can learn all those kinds of things. You can even put the AI against the AI to kind of do some tactical maneuvers and see, how it would respond to a character that way. So again, intro behavior learning algorithm does not help an autonomous character work out that it needs to do something very different. It just does the things that we've trained it to do. All right, so it does it better. That's what intro behavior is, and that makes sense for us from a machine learning perspective. Then there's inter-behavior learning, and that's kind of the frontier for what we're doing. It's learning of behavior, kind of qualitatively, and what that means is, here's some examples. A character that learns the best way to kill an enemy is to lay an ambush. So now they're learning without me telling them what to do. They've kind of explored the world, and they're learning from scratch. We're not telling them exactly what to do. They're figuring it out, okay? And it can be very surprising what autonomous agents can come up with when they're self-trained. Okay, so they explore the world. They might even do things that you don't expect them to do, like bargain with the player as opposed to attack them. Okay, that's kind of a different thing that they can do. And then this kind of thing is really difficult to come out of the lab. All right, why? Because it may not really be practical. Practical usages of this thing are very challenging. So that's the kind of stuff that we might have issues with. But it's neat, and it's something that's kind of bleeding edge, if you will. One of the problems with machine learning in general is this idea of overlearning or overfitting. And it means that, let's say, for example, your AI agent is exposed to a number of experiences or epochs. I make it run around in its terms, in its own time frame. We make it run around for, as an example, 10 years of game time, as an example. Just let it run. And what ends up happening is it learns to respond to specific situations really well, but it sucks at everything else. There's a great example of overfitting or overlearning. We don't want that to happen. We want it to have general knowledge. We want it to have a general idea of what to do and able to cope in a wide variety of situations. One of the kind of techniques that are out there that are really vulnerable to overfitting or overlearning are neural networks. So that's one thing we have to watch out, because they're really great at doing things like classification and trying to figure out what the next thing to do for the problem is, making a decision, that kind of stuff. But if you see the same condition over and over again, depending on the size of your data set, it might lead you to, the AI to do the exact same thing every single time and really respond well to one kind of thing, but then be lost in other circumstances. And that's not what we want. So that is definitely a vulnerability or an issue. So what we really want is we want them to have something called decision learning. Okay, so kind of a mix of decision making, which is what we've been talking about over the last few weeks, with decision trees, behavior trees, state machines. We've talked about goal-oriented behavior, value systems, all kinds of stuff that we've talked about over the last little while. So combining that, make really good decisions, and that's what we want them to do. We want the machine learning algorithm to hit on those decisions without going through a particular, kind of a tree. I have some conditions I'm going to throw at it, and it's going to respond, but it's going to learn when to do those things and where to do them, as opposed to always to do the exact same thing all the time, which is kind of an interesting way of using machine learning and in combination with decision making. So again, it's going to learn when to use one steering behavior over another, when to activate an animation, or how to enact high-level strategies in a war game combined with other autonomous agents, which is kind of interesting. So what we do is we give it a set of observable values, okay, and that it can get from the game level. Think about the game level as the state of the game or the state of the world. Game state is also what we call it. And this may include things like distance to the nearest enemy player, or other autonomous characters that are enemies, the amount of ammo left, the relative size of each player's army, and so on. And what we want them to learn is to associate decisions, So I want to flee. I want to, wait behind cover. I want to do all those things we talked about in assignment 4, right? With observations. So now my observations are beyond a simple sensing suite. It's not about radius and line of sight anymore. It's about other things. What is the size of my character's army? How strong do they look? How do I feel, right, about those kind of things? There's a lot of things that you can put in to make it more realistic in terms of how the AI responds. Over time, what we want them to learn is to the decisions that they make to fit with the observations. And the whole idea that I guess the desire or the problem we want to solve is we want it to improve its performance over time by having more and more experiences. So when we think about experiences for an AI, we want to train the AI somehow. And we're going to get into that next. How do we do that? So there's 2 types of supervision. We've talked about this earlier this semester. Actually, I think it was the first day when we talked about an intro to AI. What is AI? We're not talking about Terminator type AI, right? Where they're, or some kind of general artificial intelligence, which is like the singularity that people are afraid of. We're not talking about that kind of stuff. We're talking about different learning mechanisms. And there's 2 types of supervision. Think about feedback. I want to provide feedback or a learning mechanism to my machine learning agent. How do I do that? I want to provide feedback in terms of two flavors, if you will. Either weak supervision or strong supervision, okay? Let's talk about them again, just to revisit those things from earlier this semester. So when we think about strong supervision, it's like I want to give the AI a set of correct answers. This is what I want you to do. And then what we do is we as programmers associate a set of observations, if they observe something, with a set of good behavior. We want them to do these things, these positive things. And what the learning algorithm does is it learns to choose the correct behavior given the observational inputs. Okay, that's strong supervision. And these correct answers are often provided by a human player. Sometimes we even get the AI to observe the human player playing the game. Okay, so what they do is they observe what the human player would do. I mean, of course, we want to give it an expert. We want to develop an expert system or a player, give them the opportunity to watch different kinds of players, a novice, someone who's pretty good at the game, and someone who's an expert at the game. Okay, we want to create different levels. And what they do is they keep track of these sets of observations and decision pairs, right? And so that they can learn to act the same way as the player is acting. So again, that's strong supervision. We're really imposing our idea about how the AI should play the game, whatever the game is, okay? Weak supervision, on the other hand, is we don't give a set of correct answers to the AI at all, right? Instead, we give some feedback as what a good action is compared to a bad action, some feedback, and then, but more or less, it's commonly provided by an algorithm that monitors the AI's performance in the game. And if the AI gets shot, the performance monitor would provide negative feedback. So we have a performance monitor, which is another tool that's actually watching the game in real time for the AI. And it's going to say, no, that was a bad action. No, yeah, that was a really good action. You gained health there. You gained resources. You just, you killed an enemy. You built you expanded your base, or whatever the monitor is going to do. And the monitor itself gives it kind of less guidance, and so the AI learns on its own. The AI agent learns on its own, and things like if the AI constantly beats its enemies, then feedback will be positive. But if it keeps dying in certain situations, the feedback will be negative to not perform the same actions. Okay, that's the idea. So weak supervision. So again, strong supervision. We talked about this earlier this semester, first day of class, which was it's easier to implement and get right, but it's less flexible. Weak supervision. It can learn right and wrong for itself, but it's much more difficult to get right because we need to train it for a longer period of time. Sometimes we need to unlearn, make it unlearn the things that it's learned because it's overfitting. There's a lot of issues with weak supervision, and it all comes down to creating the right balance, truly the right balance. So there's a bunch of different common AI learning techniques. The 3 that you may have heard of or you may hear in the future if you pursue AI as a, kind of an area of interest. If you want to be an AI programmer or an AI designer, something like that. There are naive Bayes classification. It's again useful for classifying discrete categories of objects or labels, if you want to call them features. It's intuitive and deductive when it comes to its interpretation. There's also neural networks. We talked about this as well, which is again used for classification and prediction. It's not as intuitive, and there's no explicit behavior, but it can be done implicitly, which is kind of interesting. And then, of course, there's reinforcement learning, where we want to think about for our games. That's where we want to focus on. Neural networks and naive Bayes classification, interesting for machine learning problems. If I want to look at a data set that I want to solve, maybe not as useful. I'm just going to put that out there. I'm not saying it's not useful. Maybe not as useful at this current time of the recording for machine learning agents. Okay, maybe we can use reinforcement learning for that instead. So let's talk about reinforcement learning a little bit. It's the name given to a bunch of techniques for learning based on experience. Okay, so in its most general form, really, really simple, it has three components. One is the exploration strategy. So what it's trying to do is explores the game world. It's got some kind of reinforcement function, some algorithm that we're going to use that gives feedback on how how good each action is to perform. And then the third one is the learning rule that links the two things together. Okay, there's a learning rule. And each element has different implementations and optimizations depending on the application. Okay, so the idea is, we want the AI to explore the game world by itself, gain some experience, and we want to do it offline a lot of times. So using reinforcement learning is not something that we normally do with online learning. It's an offline learning technique typically. So here's the problem. We want a game character to select better actions over time. What makes for a good action may be difficult to anticipate by AI designers. We don't know what that is exactly, especially if you're a level designer and you put your level together. And it may depend on the way the player acts, or it may depend on the structure of random maps. It could depend on the mechanics of the game. A good example of that is, and I'm thinking something more complex, like Magic the Gathering. If you ever anyone out there play Magic the Gathering at all? I'm just putting my hand up. I mean, when it first came out, Magic was awesome. Okay, and it's still awesome today. But really, I'm going to go really way back. Back in the day when Magic first came out, it was like a chess game with cards in many ways. That's how I feel, how I felt about it when I was first playing it. It's like, but more than that, I'm going to stack my deck, and I'm hoping, probability-wise, that the cards that I want, to come out, my strategies are going to come out, and I'm probably going to put at least 4 of the same type of card in there if I want that card to appear. That's how it used to be, anyway. When I'm playing Magic, right? The idea of an AI agent learning to play Magic, I want you to think about that for a second. There are so many combinations that can work well. Sometimes when an AI agent, if you want to create an expert system to always beat the player with the right combinations, it's not just about playing the game, but also constructing the deck. So imagine if the AI agent could learn to construct the best deck based on the current Magic set that's out there right now, the current standard version, whatever the standard set is, or within range of all the standard sets and the new sets that are coming out. So as soon as the new set comes out, the AI agent incorporates new cards into its deck building process and creates a deck on its own, as an example, that it thinks is going to be effective against other players, human players, other AI agents, and so on. This idea of creating better actions over time is not just about in gameplay, but also the setup. So think about that complexity, and that's the thing that we want to be able to do. We want to be able to give the autonomous character free choice of any action. That's what we want them to do, and the ability for them to learn from their mistakes, things that they've tried, different combinations that they're trying out there, as an example, and learning from the probabilities of their choices as well. So example, I'm building a deck. There's no guarantee that this is going to, the deck is going to turn out in terms of probability. Over time, think about the ML agent, what they can learn in terms of deck building and play and gameplay, what to do, when to attack, when not to attack, assessing the other person's, how their deck is coming along. As an example, sometimes it's just a mulligan, right? And even though you may have mulliganed already, and over a couple of turns, you realize, wow, man, this strategy that I have for some kind of deck that I want, to use, this new stratagem that's come out with the latest standard set, it's just not working. Even though I've read about it on the forums and I've tried this stuff, I put together decks that people have talked about and all that kind of stuff, just not working for me, right? And it can happen even with an experienced player. It's just the luck of the draw, kind of thing. It just can happen sometimes. But for the most part, if you're a really experienced player, you can mitigate some of that stuff. You can kind of figure out, you have backups, you have ideas of what to do when this kind of thing doesn't happen that you're expecting to happen. So that's the kind of stuff we want the AI agent to be able to do, to be able to have some kind of sense of, okay, I got this plan. Here's my main plan. Here's my backup strategy. If this doesn't work, I want to go to this, and make those decisions itself. That's awesome. If we can get to that point, guys, we're going to have amazing, incredible, journeys and amazing procedurally written stories coming forward. Are we there yet? Not quite, but that's the problem that we want to solve. So again, the quality of an action is the problem. How do we clarify what the quality of a good action is? So if I want to give the machine learning algorithm a sense of, this is a really good action to perform, whatever that good action is, it's easy for us to make an algorithm to give good feedback when the autonomous character collects a power up or kills an enemy. That's easy. But the actual killing action may have only been one out of 100 possible actions that led to that result. So there's almost like, I want you to think about this almost like as a cause and effect, right? So I have a set of actions. It's actually in the real world as well. Let's look at the cone of future possibilities, I like to call it, right? So you and I are here at school right now, and we've made choices to do this. I've made choices to be a professor. You've made choices to be a student in the course. And there's a bunch of other choices that led to those choices. It's not something that just came about out of the blue, right? In fact, if anything, if you think about it, us as people, we are again, this is a little bit philosophical, but we are a product of all of our choices, right and wrong. If you could really generalize a choice as being right and wrong in real life, right? Because sometimes you might think, well, that was the wrong choice, but was it? It was the thing that got you to where you are today. So that's, again, think about trying to clarify for a computer program, what is the right choice? What is the quality choice from your limited experience as a human player? It's difficult to do. And this is where, again, we come up with this more strong supervision. We might have a stronger hand in getting the, giving it the original, kind of the performance policy, or think about this, the reward policy that we want to give the AI at the beginning is going to be heavily influenced on our experience a lot of times. So again, what we'd be able to do is we'd like to be able to give very patchy information, as an example. And then what we want to do is the autonomous character should learn that all the actions leading up to the event are also good things to do. Good example is you guys finished high school. That was a good thing to do, right? And you decided to come to George Brown. In my opinion, that was a really great thing to do. There's a bunch of actions that led to you doing what you've done today. That kind of led to your successes and some challenges that you've had too, right? So, but I want to classify all those things, almost like a cascade of actions or a hierarchy of actions and behavior as good things to do that led you to this particular point in time. The same thing for the problem that we have with autonomous agents. So then what does reinforcement learning do? It models the environment as a network of states. Okay, let's suppose all states I, let's say as an example, right? Each state has an associated reward, right? So we have a reward function, and we pass that set of states into the reward function. So for every state, we have a reward state value pair, if you will, okay? And we want to move from state to state by choosing an action, some kind of action that we're going to get to the next state. And hopefully that next state is, the given state is, the initial state that we're in. And we want to get some future state. And that future state should have a higher value or better quality than the state we're in right now. Okay, so we have a game world, and the game world has a certain state. The state of the game could be your player health. It could be a bunch of other stuff that we want to track as an example. And we want to position the AI to be in a better state in the future by taking some set of actions. Now we're going to get into a little bit of math, but keep in mind about this reward function, actions, and states, and how they all map together. So reinforcement learning then is, specified by this problem: how to find an optimal choice of actions for each state so that we obtain the greatest rewards over the long run. And this is a little bit different when we think about how reinforcement learning doesn't care about short-term rewards. It cares about long-term rewards, or the long game, if you will. Again, here's something that happens. If you ever play with a chess player that's inexperienced, they want to get the win as fast as possible. They want to do that 4-move checkmate. They want to exploit your inexperience as quickly as possible so that they can win. Okay? But when they know that you're just as talented as they are, let's suppose, or that you know the game, doesn't matter. You can sub in chess with some other game, right? Then, these better players are in it for the long game. They're in it for, knowing that you're a good player. And the idea, their belief is that every player that they're working with, when they first sit down, across from somebody, that player is just as good as they are a lot of times, right? So some of the best chess players, and I've talked to some when I was involved with chess tournaments when I was much younger, right? They remove ego, and actually some of the coaches, the chess coaches in tournaments, they tell you, remove your ego, get rid of that. We don't want to think about your ego here. This is not about that. Think about the long game. Think about how you're gonna defeat someone that is just as good as you are. Okay? It's almost like it's best to play against yourself as often as possible, right? Because that could be a very long game that you may not win. Hopefully, if you play it right, you're going to come to a stalemate. Sometimes, though, you realize you made a wrong move way back then against yourself, and now you know how to win, and it's very difficult to not have a bias, right? So that's the idea here. So again, optimal choice of actions for each state so that we get the greatest rewards over the long run. So here's an example of how this maps. I have an initial state 1, and I pass my initial state to the reward function. We have some kind of action that's going to lead us to a second state. Okay, this is the idea that it's going to have. And we're going to take that second state, state 2, and pass that into the reward function as an example. Notice that it's like a linked graph, so that there's some states that can only get you to some other states. I can only go from state 1 to state 2, or from state 1 to state 3. Really depends on action 1 or action 2, depending on which action I take as an example. So this idea of state mapping to reward through action is the idea that we want to use with machine learning. So what if we were only interested in the immediate rewards? And by the way, there's a great example of immediate rewards. We've seen that this semester with pathfinding, okay? Do pathfinding algorithms like A*, I want to ask you this question. Do they really look at the long game? Do they really look at the long-term rewards, as an example when it comes to pathfinding itself? What do you think? So think about A*. What does it do, right? It's thinking about the shortest path, right? Is that really thinking about the long game, right? The shortest path isn't always the best path, right? And this is the difference when we talked about this. We're not talking about, immediate rewards here. Best path, what the heck is that? Shortest path, we know what that is, right? That is like the shortest path to a destination. But what's the best path? Well, here's an example. Consider this network. I have an initial state 1 as an example. And the reward right now that we're in, from the reward function, when we pass our state 1, the state of the game, into the reward function, we have 0 rewards. So we're in kind of a state where we're at the state of 0, a foundational state, if you will. We have 2 possible actions to take, action 1 and action 2, right? And if all we cared about was this initial state, like the next state reward, which one would we go to? Well, it's clear that the one that I'd probably want to go to when it comes to, the next state, if you think about this, is state 2. I want to go from state 1 to state 2 because guess what? The reward function, if I look short term, is telling me that I'm going to get more rewards from state 2 than I'm going to get from state 4. So state 2, state 4. Those are the two options. I have action 1 that's going to take me from state 1 to state 2, and action 2 that's going to take me from state 1 to state 4. Nice. So I choose state 2. Now, using this graph, the only action I can take is going to lead me to state 3. That's the next action that I can take. Well, guess what? State 3, it's going to remove all the reward that I just gained from going to state 2 in the first place. So actually what's going to happen is I'm going to have 0. My reward state is going to be 0 at this point. And the only place I can go back is back to, with action 4, back to state 2. And now I'm in this loop. I'm in this loop where basically any action reward is being nullified. The next action, I might gain temporarily, I might gain a reward, and then after that, I'm going to lose everything again in the next action. This is not a great loop. This is not a great feedback loop at all. And this is kind of an example of short-sighted behavior. It's from the initial state, I want to go to the next state that has the highest reward. That's bad, right? Here's the other option. What if I took the road less traveled, not by pathfinding algorithms as an example? I take the state action 2 from state 1 to state 4. Initially, it looks like it's not great. But then if I go from state 4 to state 5 with action 5, I gain 100 reward points. Okay, cool. And then if I go back from state 5 to state 4, the reward function gives me additional 1. So it's going to continue to grow. 100, 101, 201, 202, 302, 303, 403, 404, 504, 505, and so on. Huge rewards, but it's not something that you can see with short-sighted vision. Okay, so that's why we want the reinforcement function itself to look for long-term rewards, which means I have to look further than just a single move or single action. Now that complicates things because think about our game world we just talked about with chess, right? Sometimes you always hear the myth. You want to look at least 3 moves ahead. That's what they always talk about. Think about things about 3 moves ahead. If you take the state of the game of chess, or let's even go further than that. Let's go with something that you guys know even better about, Magic. You're sitting across from the player, your opponent, and you have a series of moves, and you're trying to predict 3 turns ahead what's going to happen. Is that really possible to do? What do you guys think? You guys play Magic, Lucas and Hansen. Do you guys think you can look 3 moves ahead and trying to predict what's going to happen with the cards? What are your thoughts? And I'm putting it out there because, right? It's possible. It might. Certain hands, the way they're dealt to you, the way that your opponent is playing as well. It's possible, but it may not be. It really depends, and that's the key. It maybe depends on what you're doing, the type of deck that they're using. If it's come out, if you recognize the type of deck, if you're an experienced player, there's lots and lots of things to get you to look forward. And it's hard to look forward 3 turns for us. 3 turns or 3 moves in a turn-based game. It's tough for us to do that. But we're asking the machine learning agent to do that. We're saying, hey, we don't just want to know what you're going to do now. What's the shortest path to the greatest reward? We don't want that. We want the greatest reward over time. What is the best set of actions to get us the most reward over a fixed amount of time, whatever that time is, and usually not 1 turn. Okay. So again, going back, reinforcement learning is unsupervised, right? So it's weak supervision. We can train it if we want to make it more strongly supervised, but that takes away the kind of the flexibility that we want from reinforcement learning, the adaptability, right? And so what it does is it acquires knowledge or experience about the world independently. It's not something that you normally train it to do. So there's no explicit instructor to train the system. The system trains itself. And what we wanted to do is we wanted to do 2 actions, right? And it's almost like kind of a buzzword that they use when it comes to reinforcement learning. We wanted to explore and exploit the environment. Okay, so explore and exploit. Those 2 things, when we think about it, are the things that we want all machine learning algorithms to do, especially when it comes to reinforcement learning. Okay, and we wanted be able to handle unpredictable situations. If the player does something that is less than optimal, okay, a lot of times, a lot of AI simulations are made to predict that the player is going to do the optimal move. But what if they do something weird, something that the algorithm doesn't, hasn't predicted? They do something that is less than optimal. For example, they make a sacrifice. They take fire in order for them to get some other reward. That is something that is not as predictable as going behind cover. Going behind cover, if they get hit for a player, that's a very predictable action, right? But taking cover while you're going for some kind of goal or reward, that is less predictable for an AI when it comes to looking at what you're going to do, right? So we want the AI to be able to handle those kind of situations where we can kind of observe, make observations, and connect decisions to actions. Okay. So what we want to do again is for reinforcement learning, we want to model the environment as a network of states. Now think about what I just said, a network of states where each state connects to another node. Think about the state of the world as it is right now in a game world. Let's go back to that Magic the Gathering example. So imagine turn 1, that's the state of the game, whatever that state is, right? And now we want to model the next state of the game based on knowns and unknowns. So you don't know what the player what your opponent has in their deck. You have no idea, right? It's not a known game. It's not a closed game like something like chess, where chess has a fixed number of pieces and they can do fixed number of moves. Okay, that's what they can do. Still, there's lots of terribly a lot of possibilities for chess. But let's think about this for a second. I want to create a network of states from one state to the other, almost like a cascade or a hierarchy of possible decisions from this decision, from this state of the game right now. Okay. And what we want to do is we want to, provide rewards for entering a state. I go from one state to the other state, right? And I want to, there's two ways I could assign rewards. I can assign rewards based on a deterministic function. For example, I pass this, some kind of state to the reward function and I get some kind of value. That's deterministic. Every time I pass a certain state to the reward, I get the same value back. All right. Or stochastic. And remember, we talked about stochastic a little bit earlier this semester, which is another fancy word for random, a little bit random or unpredictable with a little bit of probability baked in. How about that? Where we have, the sum of all probabilities for each reward as it's mapped to a set of all states. And we kind of pass the state into the reward function, and we're going to get some value, based on the probability, kind of that we use. And all the values, let's suppose there's a bunch of different options. They all map up to, to a value of 1, which means that I take all the different possible actions. Let's suppose I have 3 actions, and I want to select each of those actions randomly, right? And so I assign some portion of 100% probability to each of those actions, okay? An example would be I want to, maybe, if I'm playing chess, I want to move a pawn forward, and I'm going to give it, in a particular game state, I might give it a value of 30% chance that the AI will choose that value. So not as deterministic, but probabilistic. It's like, okay, you know what? It's probably a low chance that they're going to move a pawn forward in this particular game state, right? And then maybe we'll say that there's a 40% chance that they're going to use, the knight in an attack or defense posture. So that's like 70 total. So 30% for the pawn, 40% for the knight, and then we have 30% that maybe they're going to move the queen into a risky position in order for them to draw out something else. Maybe that's going to be only 30%. So that's 30 plus 40 plus 30 adds up to 100%, or a value of, when we look at a value range of 0 to 1, where 0 is 0% and 1 is 100%, it all adds up to 1. So 0.3, 0.4, and 0.3 all adds up to 1. And that's what we do. That's the probability matrix that we can create for all sets of states as they're mapped to reward functions. Whew, right? And if that's kind of funky, transition from states. So let's say the state transition to a state, to the next state, the next state is t plus 1, the current state to the next state, is by taking some kind of action, right, at time t, and determined by some probability distribution, when we say that, some probability function, okay? And the overall goal is to optimize our rewards navigating through the system. That's what we want to do, okay? So again, world is a network of states. I'm going to go from one state to the next, and I want to look not just to the next state, the best state that's around me, but for all possible states from, or to some level some deepening, that we want to go as X number of iterations forward, some turns ahead, right? We want to look for to have a longer term reward from the current state that we're in compared to short-term rewards, because short-term rewards may make an AI short-sighted and they can be tricked. So really the reinforcement learning objective is, again, finding the largest long-term rewards obtained for entering certain states. That's what we want. And what we need is a policy function, which we use to map states to actions. And the policy function is denoted by pi, the Greek symbol pi, where we map the state into the policy function, and the policy function is going to give us an action back, right? So we're going to say, hey, based on the policy function that we have a set of states. We can also make it that's deterministic. We can also make it stochastic, where we pass in both a set of states and actions, and we have a probability of which action is going to come off based on the current state that you've passed into the policy function. Okay, and what we need to do is evaluate how good our policy is, and that's called. We actually saw this before when we talked about utility AI, our policy value estimation, or PVE, if you will. So what the heck is a policy? Let's talk about that in a second. So policy value estimation, it's a good policy picks actions that move us into states with good long-term reward. So again, going back to this diagram, we want a policy to say, hey, guess what? If you go from state 1 to state 4, long-term, you're going to have better rewards than if you went this way. Okay, but it's going to explore both states. It's going to do both. It's going to look at this one, and it's going to look at this one as well and say, you know what? I've got more rewards doing this set of actions. I've got an action. I've got an action. I got to do the same action over and over again in a recursive way in order for me to gather rewards. That's what I want to do, right? So again, we want to be able to evaluate future potential paths, not just short-term paths, not just a single connection. Okay. So the way we set up our policy value estimation, right, is, again, the goal is long-term rewards. Reward for being in the current state and all future rewards possible to obtain from that state. Again, going back to real life, it's almost like if you could look at the cone of possibilities and predict the future, okay? If I could move my game state forward in time, right, a number of turns, right, and then go back and say, you know what, this is the right thing to do based on my past experience. I'm going to do this. I've seen this game state before. I've walked around this path before, and I know by understanding the game world that if I go down this patrol path, I'm going to be safer than if I go down this patrol path. Even though this patrol path is closer and it looks like it's not as difficult terrain, this one over here is better for me from a reward perspective overall. I'm going to be able to ambush the player better towards the right side of the path compared to the left side of the path. So when we look at it, we can calculate long-term reward by using some kind of function that looks like this. So our reward t, right, is equal to the current reward. So again, this formula actually is for a single instance of traversing our world, where Ri is the reward at time I. So that's the first thing. And gamma is the discounting term, and that's the discounting term is between 0 and 1. And what this does is the discount term actually creates almost like it creates a value that's a multiplier or a factor, if you will, that's going to be reducing the reward over time, right? So it's not going to be 100%. You're not going to. There's no possibility that you're going to get 100% of the reward from time 1 to time +1 to time +2 and so on in the next turn, the next turn, the next turn going forward, right? So we don't want a single instance trajectory rewards. We want long-term value of choosing a state. Again, example, what future rewards are possible from going from that state to another set of connected states in the network. Okay, it's a really interesting way of thinking about things when it comes to how this is set up. So again, think about this. How do I know what all future potential rewards are? So again, long-term rewards for all next states Sj of current state Si, right? Example, if I pass in into our value estimation function the next state, which is Sj, what is the value of that in my policy? Should I go into that next function or not, based on the policy that I'm using, right? So each next state Sj should be weighted by some kind of probability, right? Which is the probability of going to that next state. What is the probability of me going to that next state based on my current state? And when I say probability, it means that what is the AI going to decide to do based on its experience, and the given game state. It's not always deterministic, is what I'm saying. Okay, so thus, when we look at some of these functions, we're going to just look at a set of formulas that are going to expand to give us some kind of policy value estimation function at the end, right? Where we say that if I pass a set of states, the next state j, to the policy value function, it's going to return a reward of based on the current state that we're in right now, plus all future possible rewards, whatever all the future possible rewards are that's connected from one state to the next, right? And again, based realistically on how many iterations or how many epochs we're going to go, how many turns I'm going to let go forward, right? Because the deeper we go, the more options we have when we kind of trying to predict the next set of moves. There's two things that are going to happen. The probability that we're going to be correct is going to be less and less, right? Because we cannot predict what's going to happen in the next state, the next state, the next state, unless we've traversed this world and we've seen this kind of state before. Okay, that's one thing. So that's really, really challenging to do. So this function here, where we say when we pass our next state to the value estimation function, it expands to when we say all future possible rewards. We can kind of write it as the current state passed into the reward function plus all future rewards. This is what it would look like. Okay. And then when we take that function there, this is a recursive formula, and it can be written as a vector, right? A matrix vector equation, where we say that the value estimation function, again, it has magnitude and direction, the direction from one state to the next state, and it has a reward vector, and the reward vector is added to a probability function that maps to the next value that we're going to get from the matrix, all right? Where the vector v and vector r are column vectors of state value estimates, right? So where, what's the next state that we're going to get? What, depending on the policy, which is almost like our map of goodness for the entire game world, right? And rewards, okay, that's what they are. And then again, P, capital P, is a conditional probability transition matrix, with rows being the current state and columns being the next state. So what is the possibility that I'm going to go to from this state to the next state based on my policy value estimation function and the rewards? That's how it works. So it's quite complex, as you might see. I'm going to skip this slide. So it talks about how to build your value estimates and so on. It talks about how to do that. And basically what these next slides do is they derive, into a specific policy function. So where we pass in, like we said before, a stochastic, it comes up with a kind of a set of probable actions, based on the state of the game world. That's the policy function, and the next actions that are connected to it, to that particular state. Right, so not all, there's not every possible action isn't possible for every game state. Some actions are blocked. As an example, for example, if we have if there's no ammo, kind of within a particular range next to the autonomous character, then getting ammo for their gun isn't even a possibility, So some of those actions are blocked and they can't be passed into the policy. There's no value estimate from doing such an action. Sure, you can reload. That's a possible action for you. But if there's no ammo, that action is not possible for you at this particular point in time or that game state, the state of the game that you're in. Okay, so again, the general approach is we currently have some kind of policy function where we pass in the current state and a set of actions, and a way of evaluating a policy with the policy value estimate. That's a function or an algorithm that we kind of described in some detail above, and I'm not going to go into it. Again, a little bit out of scope. And we want a best or optimal policy that gives the best long-term rewards. How do we find it? How do I get that policy to be better and better? Because the policy function is what's giving us the rewards or kind of pushing us to that next state. It's through something called policy iteration. So we start off, like who writes that policy in the first place? Because the policy is like, this is good and that's bad. That's what a policy is, right? So it's going to basically kind of feed into the reward function. That's what it does. So here's the way it can be done. We arbitrarily choose a policy. So we just make a policy up. And what we want to do is perform a policy value estimation. We follow the policy for a large number of steps, okay? And then we solve the value estimation formula for that policy. We kind of figure out what is the value from doing this action on this particular set of states and all future possible actions for to get the maximum reward, right? And then what we do is in the third step, we perform something called a policy improvement, where we actually overwrite the original policy, right, with the stuff that we've learned, okay? Now, there's a danger here, and I want to talk about this as well, is there's a danger of overfitting, right? So depending on how, we use the policy improvement function, we can actually create that overfitting or overlearning situation. And that's why we have that discount term. The discount term, what it does, it says, okay, you know what? It's not 100% chance that we're going to do this every single time. So it creates a policy matrix, almost like a table, if you will, that allows us to make proper decisions based on the current state of the game that we're in and all future rewards based on the next state that we're going to take. Phew. So we keep on doing this loop over and over again for several epochs, if you will, or several iterations. And so until we have a state that we're happy with when it comes to the policy, the AI is reacting in a predictable manner to some degree based on the game world. So if I see a game state, we can probably figure out that the AI is going to adapt to that particular situation. Notice I didn't say it may not do the exact same thing every time. It may not go hide behind cover every single time perfectly. It might do something else. It might go for that other thing, like grab a health potion, as opposed to hide behind cover. And it really depends on the experience that it's gained by using the policy, the policy value estimate over and over again. All right. I'm not going to talk about this. I'm going to move on to implementation. So things that we need to do, we need to set rewards for every state. So that's whenever we use reinforcement learning, every single time we're in a particular state, we want to set the rewards. We want to determine a discount value gamma and choose an initial policy function like we talked about before, right? Even if it's a bad policy, it doesn't matter because we're going to have that policy iteration step where we kind of do a policy improvement. We're going to do a policy improvement, and that's part of the learning, right? We're going to improve the policy, almost like a matrix of decisions that we're going to make based on current states and all future possible states. That's what we're going to do. And one of the things is if there's two options, right? If we explore too much, we might overfit. If we don't explore enough, right, then we have a poor value estimate, right? So we kind of have to find that sweet spot. And that takes, I'll be honest with you guys, when I've done reinforcement learning in the past, it takes a little bit of tweaking and trial and error to figure out how many iterations you're going to do to improve your policy value estimate, right? That policy function is super important for you to have proper rewards and actions. Remember, you're mapping actions to rewards, right? Here's the next action based on my state. I want to get the maximum reward over the long term. Okay. All right. So again, when we build a probability matrix, P, we start with the zero matrix, and then during the exploration phase, remember we talked about there's two phases when it comes to reinforcement learning: exploration and exploitation. During the exploration phase, for every transition from state I to state J, where state I is the current state and state J is the next state and all possible next states, we increment the probability ij by 1. So if, for example, I realize as I'm exploring, I've been there before, I have a probability matrix where I say, well, what's the chances that I'm going to do this again, right? I increment it by 1, so I've gone to that particular state. From one state to the other state, I've done this before, right? And then at the end of exploration, we want to start exploiting. We want to say for the set of all possible states J, right? We want to kind of calculate the probability of ij, where what's the probability of me going to that next state again? I'm going to have some value between 0 and 1. Okay, and this will convert your matrix into a probability matrix. What we want to do is we want to create a probability matrix of where I'm going to be from one state to the other, and that probability matrix is going to be based on the value estimation function and our policy. Wow. All right, so that is quite complex. Reinforcement learning, at a very high level, when we talk about this stuff, it's like, what did he just say? Right? It's tough. Things to takeaways for you guys to think about. Overview, again, if I was going to go back. We want our AI to explore the world. As they explore the world, they figure out what's good, but they have a foundational step where they're given an initial set of what we think is good, even if it's a terrible policy. We give them an initial policy. Think about it as a scratch policy, something that they're going to overwrite over several iterations. When they do something, they have some kind of monitor that's going to basically tell them that what they've done, the action that they performed, is a good action. Every time they make a good action, we update the policy to let it, so that when we get into that same state or very similar state of the game world, we know that the next set of actions, not just from the current state to the next state, but all future possible states are going to lead to a better reward over time. That is what we want to do with our reward function. So here's another approach. That was a very complex approach. There's another approach that people use, and it's something called Q-learning. So Q-learning is a reinforcement learning algorithm, or technique, if you will, but it treats the game world as a state machine, okay? So the entire game world. And at any point in time, the algorithm is in some state, whatever that state is. And this is interesting. Might be something easier for us to kind of implement than full reinforcement learning, okay? Reinforcement learning takes quite a bit of time and effort to do. And like I said, it takes training, iteration, and you have to kind of develop things like the policy matrix, the probability matrix, and that whole mapping of observations, actions, and states. So being able to observe the world and determine what state the world's in, that's kind of a key. I need to understand or kind of recognize the state of the world. And then after I recognize the state of the world, right, whatever that state is, I want to, create a set of mappings. Right, I want to create a network of states from one state to the next. What I'm going to do next. Okay, and this is kind of abstract and esoteric, the stuff we're talking about. We need some more hard-coded examples, some examples so that you can get what we're talking about. So, so one thing is, at any point in time, the algorithm, this Q-learning stuff, is at some state, whatever that state is, and the state should encode all the relevant details about the character's environment and internal data. So this is details for you, right? So if the health of the character is significant to learning, maybe this is an important feature that you care about. And if the character finds itself in two identical situations with two different health levels, then it will consider them to be different states. So every property that you care about creates a new state. Okay, so almost think about this as X dimensions. The more states you have, the more properties or things you want to keep track of that are important to your autonomous character, the more dimensions you add in an array. Think about this like multi-dimensional array where every new property creates another dimension, not just, two-dimensional array, but a multi-dimensional array. So again, for example, if I had 5 things that I was looking at, I would have an array of 5 dimensions deep. That's the complexity we're talking about. Why? Because for every possible property, there could be different values of the other properties. Example, if I care about health and ammo, that's a 2-dimensional array, right? Where I have mappings between my health value and my ammo value. If the only things I care about are those 2 things, it's quite easy to kind of understand what the next states are. If I have a low ammo and there's ammo nearby and I have a high health, then my next set of actions might be get ammo. Okay? Anything that's not included in the state cannot be learned. So if I don't include health as part of my dimension that I care about, we won't learn anything about health. We won't know anything about health. We won't care about health. The AI won't do anything about health, okay, if we don't put health in there. So anything that you don't put in there, it's not going to do. It's not going to care about. It's not going to keep track of. It's not going to iterate on. So in a game, the states are made up of many factors. Example, position, proximity to the enemy, health level. Each of these factors is a dimension. Q-learning does not need to understand the components of a state. We don't care about, all the components. As far as the algorithm is concerned, they just need to be an integer value, the state number. So if I state number 35, state number 35 could kind of convert to, a bunch of different factors of different properties adding together. So example might be something like, I have health of this value, I have ammo of this value, I have food of this value, I have, my position is this value, right? My enemy is at this value, wherever the value is, right? And I have, right now, I'm just talking about 5 dimensions that I'm looking at in terms of how do I create that number, that state number 35. How do I create that? Okay. So we can convert from our current state of the game to a single state number. That's what we want to be able to do. So somehow we look at a bunch of different factors, we come up with one number, right? But we never have to convert back, typically. We don't have to go from that state, whatever that state is, back to real world information. We don't need to do that. So one thing to note is that Q-learning is known as a model-free algorithm because it does not try to build a model of how the world works. It doesn't do that. It's not like reinforcement learning in that way. It simply treats everything as states. Everything is a state, okay? Algorithms that are not model-free try to reconstruct what is happening in the game from the state that it visits. So reinforcement learning is a good example of that, where it tries to simulate the game world and the next step, the next step, the next step. We're going to transition from this state to the next state. I'm going to recreate the world or remodel the world from one state to the other. Q-learning doesn't do that, right? It's easier to implement. For each state, the algorithm needs to understand the actions that are available to it. And again, like we said before, not all actions are available at all times. It really depends on the game itself. Okay. So after a character carries out one action in the current state, the reinforcement function should give it feedback. Did I do good? Did I do bad? Is it positive what I did, or is it negative? And what we can do is we can create a mapping function from a range of -1 to 1. -1 to 1 is really great because instead of going from 0 to 1, where 0 is 0% and 1 is 100%, you might have really negative actions, things that take away from your reward, right? Like, for example, if your character got killed, autonomous character, that would be a -1. You don't want that to happen again. So you create that mapping, if you will, of all possible actions based on the state that you're in. So again, the other thing is there's no requirement that for every reinforcement value, whatever that value is, to be the same for every time an action is carried out in a particular state. So there might be some other contextual information that's not used to create the algorithm state, something else that's doing that. As we saw before, the algorithm cannot learn to take advantage of something that it's not part of. So example, we're only caring about elements or dimensions that we list inside of the reinforcement function, right? So let's suppose I care about the, my health and ammo and food. But what if weather isn't something that I care about? But weather could affect my terrain, right? So even though I care about the state of the world is defined by, for me as an autonomous character, health, food, and ammo, but then there's weather, and I'm not keeping track of the weather. It could affect the availability of food, that ammo is buried, and that my position is compromised based on, let's say, lightning or whatever, right? So again, if I'm not tracking it, it's something that I can't learn about, okay? And that can change the outcome from one state to the other state, because my states may not represent the entire world with every single dimension, every single possibility. It may not include all those things. I'm only reducing it to a smaller set of properties, if you will, that I care about for my particular agent. Okay. So after carrying out an action, the autonomous character is likely to enter a new state, whatever that action is. Carrying out the same action in exactly the same state, like we said before, may not always lead to the same state of the game, and other autonomous characters in the play are also influencing the state of the game itself. So even though I might go from one state to the other, the state of the game may not be predictable based on other influences, things that we can't map, or we've chosen not to map. Here's an example. An autonomous character in an FPS is trying to find a health pack and avoid getting into a fight. The autonomous character is ducking behind a pillar. On the other side of the room, an enemy character is standing in the doorway looking around. So the current state of the autonomous character may correspond to, in room 1, hidden, enemy near, near death. So notice that I'm only talking about 4 dimensions, right? I only care about in room, what room I'm in, the position, if I'm hidden or shown, right? Is my enemy near or not? And what's my state of health? Those 4 things I only care about. So that describes the state of my world. I'm using those 4 factors to determine the state of my world from one state to the next state. And that's the only factors I'm thinking about. Okay? So the enemy stays put so that the hide action leads back to the same state. I'm back in the same state. So it chooses the same action again, keep hiding, right? This time the enemy leaves, so the hide action now leads to another state corresponding to, in room 1, hidden, no enemy nearby, near death. That's another state. Once the enemy leaves, right, because we care about that enemy, we can learn from it. We can do a different action based on the next state of the game. Okay, so again, multi-dimensional in terms of almost like a state machine. A multi-dimensional state machine is what Q-learning is about. One of the powerful features of Q-learning and other reinforcement algorithms is that it can cope with uncertainty. And that's one of the things we talked about way early when we started talking about reinforcement learning and machine learning in general. And there's 4 elements: the start state, the action taken, the reinforcement value, and the resulting state. And what Q-learning calls these things are the experience tuple or tuple, depending on how you want to pronounce that word. Often written as SARS, believe it or not. I can't believe when I first saw this, I was like, wow, what is this? It's actually the initial state, the action, the reward, and the final, the next state is what it looks like, right? So when you look at this kind of function, that's what we want to get to. So what is the current state? What is the action I took? What is the reward I got? And then what's the next possible state based on where I am right now? So again, Q-learning, where it comes from is it comes from the quality information or Q values it holds in its Q matrix. That's what it's about. And the algorithm keeps a value for every state and an action it has tried. So it keeps all those values. And the Q value represents how good it thinks that action is to take when in that particular state. So if I'm in an enemy, I'm hidden, like we talked about before, all those things, those 4 dimensions, right? We kind of come up with a value. What is the value of staying in that state? What is the reward of being there? As an example, compared to doing something else, right? I mean, remember, we want the AI to take the next action based on the long-term rewards, based on its algorithms that we're using. Okay, so here it talks about how to do the learning itself. Again, I'm not going to go into all the nitty-gritty detail here, but really what it does is it splits the experience tuple or tuple into two sections. The first two elements, the state and the action, are used to look up a Q value in the table, in the Q table. All right, basically what it is, in the data store. And the second two elements, the reinforcement value, which is the reward, and the new state are used to update the Q value based on how good the action was and how good will it be in the next state. All right, so that's how it's looking. And so the Q learning rule looks like this. Okay, I'm not going to go into it, but basically what this looks at is we pass the state and the action into the Q Q value table, and then what we look at is what is the outcome of that based on the next set of possible actions, where alpha is something called the learning rate. And what we want to do is be careful about alpha, because at the end of the day, if the learning rate is 1, then we're not going to really learn something. We want to use a learning rate that's considerably lower. And we'll talk about kind of optimal values to set up initially. So how it works, and this is kind of at a very high level. I want you to think about this. We initialize the Q table, which is our quality table. We choose an action. We perform that action. We measure the reward. We update the Q table, and we keep doing that over and over again in a recursive loop, okay, over and over again. And so what we're trying to do, just like we did with reinforcement learning, is policy value iteration. We want to, the policy in this case is that Q table. And that Q table is something that we want to improve over time, okay? Okay, again, I'm not going to go into too much more detail, but for the most part, that is what, at a very high level, and I'm scratching the surface here of how to implement this, but at a very high level, that is really what it is, this little loop here that we're talking about. Okay, I'm going to skip forward a little bit. So we've talked about the reinforcement function in the learning rule and kind of a little bit of the internal structure of the algorithm. We know how to update the learning from experience tuples. Again, we have the current state, an action, the reward, and then the next possible action, or the future action, if you will. But it also requires something called an exploration strategy, a policy for selecting which actions to take in a given state. And it's just simply called the policy, okay? So the exploration strategy isn't strictly part of the Q learning algorithm. It goes back to that stuff we talked about before with reinforcement learning. The basic Q learning exploration strategy is partially random. And the reason why we want to make it partially random is because a bunch of reasons. One is we don't want to make a predictable AI, number one. And two is we might learn something by doing an action that we haven't tried before, right? We want to try actions, that all kinds of actions, and we want to kind of map the results of those actions in our Q table, all right? And so that's why the policy is somewhat random in terms of what it does. And sometimes this random exploration it's the main way that Q learning works. This random exploration is how the Q table is built. It's built up of random selections and random actions that can lead us to new possible rewards, or even to learn about the game world beyond the observations of an outside AI designer, right? So we're going to let the algorithm do its work for us, as opposed to us trying to create a policy to give to it. Okay. Again, it talks about this, and here in the slides, it also shows us an example of some pseudocode on how to set this up. So again, we create, and I'm going through this pseudocode. I don't like to do this all the time, but what we want to try and do is set up some kind of Q value store, where the Q value store is some kind of matrix, and it has several dimensions that we want to look at, like I said. A lot of times we can use some kind of an array or a vector that keeps track of all the properties that we care about. Okay. All right. So I've included this stuff here as an example from the book, but I also want to go kind of further. One thing that the Q value store does is it has several functions. Get the Q value when we're mapping our state in action, whatever that quality value is, right? We want to be able to get the best action, based on the state that we're passing in. So what is the best action that we know we can retrieve from the value table? So far the things that we've learned to do, and we want to be able to store the Q value, as an example, depending on the state and the action, back into the table. So that's the iterative way. So again, we want to explore, just like we did in reinforcement learning. We want to be able to explore and exploit, but we're going to do it in a more random way and less structured. We're not going to be as strict as when we were with reinforcement learning. Okay, I'm going to move on to this. It talks about tailoring parameters and the function and what each of these things mean. And it talks about how to start them off. For example, the different factors mean different things. Alpha is the learning rate. We talked about a value between 0 and 1. We don't want it to be 100%. And the author recommends something like 0.7 is relatively high, which means it's always going to learn to do that thing more often. Over time, the value can be gradually reduced until it reaches a lower than normal value of 0.1. But we start that particular thing is a good thing. Learning rate means that I probably want to try to do that action. That's what learning rate means. Gamma is the discount rate, and usually a good value to start off with is something like 0.75%. We want to discount the value of the next possible set of actions, so it's not 100% every single time. Right? We're using probability to create our matrix, as opposed to having a set value policy value estimate. We want to have the Q learning function do it for us. Okay. And row or randomness for exploration. We want to use an offline. We use this in offline learning as something like 0.2, which is 20% chance that you're going to do something that you haven't tried before, right? So again, you're most likely going to do something that you've already mapped, something that your autonomous character knows that's going to return a higher reward. But over time and iteration, as it continues to explore the world, it's going to eventually try other paths, things that map to lower rewards or potentially even higher rewards. Okay, so that's the randomness for exploration. And one of the things that we also talk about is the new, which is the length of the walk. Length of the walk is the number of iterations that will be carried out in a sequence of connected actions. And usually it's in a state of 0 to 1. Again, we don't want the larger number of actions, the more we might see overfitting, and also how it's going to take a lot longer to explore the game world. Smaller set of actions may not lead to a very comprehensive policy. Okay, so that is tailing the parameters, and when it comes to choosing the rewards, and how do we kind of reward an AI? So again, rewards are provided for two reasons, right? Reaching the goal, whatever the goal is. Again, you can combine this with goal-oriented behavior, and for performing some other beneficial action, gaining health, gaining ammo, killing a character, whatever it is, right, as an example. So again, negative reinforcement values are given for losing the game or dying, taking some undesired action that's going to lead to another set of undesired actions. So that's how we can kind of set rewards. And those things are things that we have to kind of train ahead of time. We have to tell it, at least in the beginning, what's good and what's bad. Okay. All right, so that is a very high level things, talk about reinforcement learning and machine learning in general. Takeaways. Let's talk about takeaways here. So we talked about two types of learning algorithms. The first one, reinforcement learning, is more complex, but very comprehensive, right? Again, largely used in offline learning. And then the second one is Q learning, which is a little bit more stochastic, a little bit more random, but can equally or it's a little bit more efficient in terms of how fast it can learn and create its policy matrix, or the Q matrix, if you will. For more information about these two things, please, I've shared a couple of links for you if you're interested. So some of them they're up on Blackboard. Let's take a look. If you're interested, I have a couple of links. What is reinforcement learning, as well as an introduction to Q learning, reinforcement learning, which is up online as well. Again, if you're interested in AI, take a look at these two. The articles aren't that long, and it gives you a really good high-level view of what reinforcement learning is and what Q learning is all about. Okay. Any questions around anything like this? Any thoughts? Would you try and use Q learning or reinforcement learning in a game in the future? What are your thoughts, guys? Or is the answer you're too burned out and your brain is on fire right now after this thing and you don't have any thoughts about this at all? And if it is, it's okay. Brain's on fire. My brain's on fire too, Lucas. When I look at this kind of stuff, I'm always like, wow, there's a lot of things to think about here. Could we make it simpler? There's another takeaway. Could we take the ideas that we have with Q learning and reinforcement learning and create our own policy matrix, our own way of creating rewards? Well, we have the tools for that already. We have utility AI. Utility AI is kind of a middle step. It kind of gets us closer to a reinforcement learning strategy. There's nothing to say that you can't use multiple factors, right? Minecraft server. Multiple factors, to decide, the state of the game that the character's in, right? So having almost like a, kind of a state machine that has multiple states happening at the same time, right? So, and then taking that and having a value, creating a value from, several different enumerations, right? So imagine if I had 4 different game states. This is the takeaway, or 4 different states that I care about, 4 different properties. I'm hurt. I'm not hurt. I'm partially hurt. I'm very hurt. I don't know, different layers of hurt, right? And I'm hungry. I'm not hungry. Getting hungry. I'm really hungry. As an example, that can lead to some other bad things, right? So I have a bunch of these enumerations that I put together, and then and let's suppose each one of these things, if we carefully craft our enumerations, the value that's associated with them is something that is multiplicative instead of additive. So, or some kind of value where you square the value, right? So it's not something that you're going to get. You're not going to get the same value when you combine those things all together. So you're going to get a unique state number, whatever that unique state number is, by combining all of those different kind of states together. That's kind of a way of doing it with Q learning. All right, so that's all about machine learning, at least at a very high level. Hopefully, that has given you some thoughts. As where we can take our decision making and our kind of making more realistic decisions, learning about the game world ahead of time, and so on. Or even understanding what a machine learning agent will do. If you're using something like Unity's ML agents, what do they do? Well, they do this kind of stuff. They kind of use reinforcement learning or some kind of technique to learn more about the game world and what actions to take. Okay, so that's one thing you should learn. So that's it about my talk about machine learning, but let's talk about a couple things. So questions for you guys before we go for the day. Your final presentations, are you guys ready? What are your thoughts? Hanson says, for A5 presentation slide, what does game concept mean? What should we put in there? So, okay, it's a good question. So we've asked you to put together a interesting map. We've asked you to take our requirements for creating your little AI game, but you can color that map and make it your own theme or anything else like that. For example, maybe you've made a fantasy-like theme for your map and for your game, right? What inspired you to do that? Were you inspired by another game you've played before? That's your game concept. Your game concept is like, okay, I want to take this decision-making assignment and I want to wrap it into some kind of a theme. How did you come up with that? Why did you choose that? That's what it means. Maybe you love fantasy games, or maybe you really love, you made some kind of Minecraft-like game or something else, some kind of 2D exploration game. And that's why you chose to use the map and the sprites and the sound effects and the aesthetic that you use. Okay? That's what that slide's all about. Almost a little bit of thoughts. Hey, this is why we did it. Any other questions around assignment 5? Let's swim all the way to the top. I think that's important for us to do. So if we go all the way to the top here, Again, stuff to note about um, our schedule for this week. So again, this week, remember, this is the last lecture. This is all about machine learning, giving you an insight of what that looks like. But what we want to do is just keep, remind you that there is a kind of slots for presentations. So again, if you haven't had a chance to look at the presentation slots and you haven't signed up, we're looking for when you're presenting, who's presenting, as an example. Now, group 21, and maybe this is Aiden, David, and Lucas. Maybe you guys are all presenting. I don't know what that means, if that's what it means, and that's okay. It just means that you should be practicing your presentation to make sure that you know how to pass the baton from one presenter to the next. Okay. So that's our plan for this week on Thursday. Please make sure, if you haven't signed up already, to sign up now, so you know when you're presenting. Also, please make it a point of being on time for your presentation. As again, if you're late, away, or if you plan to be there and somehow you're not, or you forgot, you won't get any marks for your presentation. One thing I also suggest, guys, because this has a bit of marks, it's worth 6% of your final grade, if I'm not wrong. Please make sure that you connect with other people in your group so that they know if something goes wrong and you can't make it, who's presenting in as a backup. You should have a backup presenter. Okay, you don't have to list it here, but you should talk with your group itself and kind of decide, hey, you know what? Let's suppose that Raul can't make it, then maybe Jack is going to present, as an example. Okay, I'm just putting it out there. I'm not saying that he will, but something like that. No, you don't. I'm just saying that this might happen, right? So, yes, you can do that, Havish, but I don't recommend it. I recommend that you only have one group member present, the strongest group member when it comes to their presentation skills, their interest in doing the presentation, and so on. But you could have multiple team members present if that's your presentation style. I don't recommend it, only because there's going from one type of presentation style to the next, different volume levels, all that stuff can make a bit of a weaker presentation. Okay. So that's it for me, guys. There's nothing else for today. One thing I want to say for those people who are watching, since this is the last lecture, is thank you so much for being a part of Game AI this semester. I know that there's been a lot that we've covered. And for some of you, it's, maybe there's things you still want to explore. You didn't have a chance to explore to your very fullest ability some of the topics that we presented this semester. Guys, it's okay. Okay, you don't have to know every single aspect of everything we've talked about this semester. The idea here is that you have now more information, more of an idea of what is possible that you can do that's been done before, that we're doing currently, kind of in the industry. And once we know what is possible, then we can start being creative. That's what this course is all about. This course is about, hey, how do I make my AI challenging and non-deterministic? How do I make it so that my characters are challenged, or my players are challenged? That way I want to come and play the game. I want to have that improve my replayability, my immersion and presence in the game, my suspension of disbelief, so I can continue playing. That's what this thing is all about. Okay? And to make your games pop that much more. So that's it for me, guys. Thank you so much. I'll see you guys, some of you on Thursday. If we don't see each other, again, marks should be in by the end of the week. But I think for the most part, if you've submitted the stuff that we've asked you to submit, and you've kind of, did your level best to meet the requirements, then the mark should be fairly decent. Okay, guys, thank you so much. And I'm hoping to work with you guys again in the future. Look for us again in myself and Alex in physics. I may have another partner for physics in September, but that's the next possibility for us to get together. We're also going to redo this course in the summer semester. So again, for those of you who need to do this again, or if you have a partner that intends to kind of do another lap of this one, we're offering it again in the summer so that you can do that much better and be more prepared for the fall semester. Okay, guys, thank you so much. Really appreciate you guys that, the people that were here. I miss some of you. Raul, I miss you. And everyone else that I haven't seen as much this semester. But thank you so much, and I'll see you guys on Thursday. Thank you. All right, take care.